but this sunspot group is very, very active, grew tremendously while it was on the far side. We see that activity right here as it rotates towards the eastern limb solar coordinate system, and that is a sort of electrical and plasma crackling and bustling activity that you usually see before high M class or even X class solar flares. So this sunspot group has already been very active over the past few days. We have our coronagraph imagery, which shows all those coronal mass ejections launching off to the left. That's again to the east solar coordinate system. Now it's going to be rotating to view. So we can expect radio blackouts on the sunlit side of the Earth anytime there's a big solar explosion from that sunspot group or another. And then if it launches coronal mass ejections our way, that could impact us if it's really quick in about 24, maybe even less hours than that, but typically 2 to 3 days. It depends on that velocity. And when you get that impact is when you get a geomagnetic storm. Earth's magnetic field undergoes these big swings in field strength, and you have these powerful electric currents that are generated all across the Earth energy onion, as I call it.
When solar flare AR430 erupted on December 4th, it was expected to be a routine event. Classified as an M-class eruption, it wasn't the strongest solar flare recorded this month, but it was still powerful enough to inject a significant stream of charged particles into the heliosphere. NASA's Solar Dynamics Observatory tracked the flare's origin near the Sun's equator and modelled its projected path. The data showed it would brush Earth's magnetic field, just enough to trigger minor geomagnetic disturbances. But within hours, deep space monitoring stations noticed something unusual. The solar flare's energy stream appeared to shift. Rather than maintaining a straight trajectory toward Earth, the flare's particles began curving inward, not away from the Sun, but toward a corridor of space that had already drawn global attention, the path of 3I Atlas. The shift was subtle but persistent. The plasma stream tightened into a more cohesive bundle, unlike the typical broad diffusion seen in previous events. This strange cohesion was the first red flag. Normally, solar particles scatter over millions of kilometers. Here, the stream was maintaining shape, like it was being pulled or compressed. Plasma sensors aboard the Stereo spacecraft registered elevated densities along the vector, far higher than normal dispersion allows. Scientists began wondering if something in space was interacting with the stream. The flare pulse moved closer to the object known as 3I Atlas, a mysterious interstellar visitor already under scrutiny for its bizarre lack of a tail, rhythmic pulsing, and high-speed orbit. And then it happened. The flare made contact. The expectation was simple: disruption, energy transfer, instability. What actually occurred left every model broken. Atlas absorbed the flare and survived, without changing its course or brightness. The solar flare never reached Earth. Atlas intercepted it. Every known comet reacts to solar exposure the same way. As they approach the Sun, volatile materials on their surface heat up and sublimate, releasing gas and dust into space. This process forms the iconic tail, sometimes stretching millions of kilometers behind the comet. The closer to the Sun, the more violent the sublimation, but 3I Atlas doesn't play by these rules. When the solar flare's plasma stream collided with Atlas, astronomers braced for the obvious. At minimum, they expected visible outgassing. At most, the object should have flared dramatically, spewing material in all directions. But telescopic arrays from ground-based observatories in Chile, Hawaii, and Spain showed nothing. No tail, no gas cloud, no diffused halo. Just a small, sharply defined point of light, untouched, unaltered. Researchers ran spectral analysis immediately. Comets typically release compounds like cyanogen, water vapor, ammonia, and carbon dioxide when heated. These show up clearly in ultraviolet and infrared, but Atlas produced no such markers. Its spectral lines remained flat, suggesting a surface completely inert to high-energy input. Some suggested that Atlas was composed of dense rock or even metal, but even metallic objects should reflect increased sunlight or experience thermal torque. Others proposed exotic materials, perhaps carbon compounds with melting points far higher than water ice. But even then, the absence of any response to an intense solar pulse is nearly impossible to explain. The data now confirms that the object did not expel any measurable dust or gas. There was no expansion of surface layers, no reflective bloom, no increased spin or wobble. This was not a passive event. The solar flare was strong enough to trigger tail formation in any ordinary body. But Atlas did not react. It simply continued on, as if built to withstand the sun itself. At the exact moment of impact, Atlas responded with a flash, not an explosion, not an ejection of particles, but a smooth, sudden brightening, like a camera bulb popping once in the dark. The pulse lasted no more than 3 seconds. Then, everything returned to normal. This light burst wasn't chaotic. It wasn't the uneven shimmer of a spinning object or the asymmetrical flare of escaping dust. Instead, the brightness increase was uniform across the object's visible surface. It rose quickly, plateaued, then faded. What's more, the reflected light was spectrally clean. No erratic scatter, no signs of material dispersing outward. Some researchers compared it to how highly conductive materials briefly emit light under electrical stress, then discharge the energy through internal channels. Others suggested it resembled the response of compact plasma structures when impacted by solar radiation, absorbing, storing, and radiating energy in a controlled waveform. This type of behavior is not only unusual, it's categorically alien to comet science. Even asteroids show uneven thermal responses to solar input. The only systems known to exhibit such instantaneous reversible brightening are engineered systems with internal damping or electromagnetic shielding. Of course, no one is officially calling Atlas artificial, but the consistency of these signatures is forcing open that conversation. The most striking part of the flash. It was not followed by any secondary event. No lingering thermal glow, no orbit deviation, no emission trail. It's as if Atlas was not hit by the flare, but instead acknowledged it, absorbed it, reacted briefly, and then carried on as if nothing had happened. A momentary blink, and silence again. In the minutes following the flare's impact, astronomers rushed to capture spectral readings of Atlas. The expectation was simple. If the object had absorbed part of the flare's energy, some of that energy would re-radiate outward in the form of heat, gas, or reflected particles. Even inert bodies release some kind of thermal echo under such conditions, but the spectrometers told a very different story. Across multiple observatories, including Lick, Mauna Kea, and La Palma, the object's light spectrum shifted ever so slightly, not dramatically, not like a heat spike or chemical burn. Instead, the wavelengths showed an even narrow band of emission, an energy envelope consistent and symmetrical, forming a shell around Atlas for just under 6 minutes before dissipating into space. What this suggests is extraordinary. Instead of releasing energy chaotically, Atlas appears to have redistributed it. The envelope, a temporary glow in polarized light, behaved like a magnetic containment field. There was no outflow of gas, no reflection of chemical compounds, no signs of phase change or ejection. This raised a disturbing possibility that Atlas possesses surface or subsurface properties capable of managing electromagnetic input, and that the object can buffer solar events without undergoing structural compromise. Objects like Earth's magnetosphere and Jupiter's radiation belts demonstrate large-scale containment of charged particles. But this was different. This was a discrete, localized event in deep space, centered on a body no more than a few kilometers wide. The energy didn't just vanish, it was processed, then released smoothly, like heat fading from a metal coil. And perhaps most unsettling of all, this redistribution was not a passive reaction. It was patterned, timed, predictable. That's not how nature usually works, unless there's a system behind it. Momentum is non-negotiable. When a moving object absorbs another stream of mass or energy, even minutely, it experiences change. This is true whether it's a grain of dust or an interstellar object the size of a mountain. That principle underpins how we navigate spacecraft, study comet trajectories, and model solar wind interactions, which is why Atlas's orbital consistency is so confounding. After absorbing a flare's worth of solar plasma, there should have been a shift, a nudge, a measurable deviation in trajectory or velocity. Solar radiation pressure alone often causes minor but detectable alterations in a comet's orbit, especially when outgassing is involved. But Atlas didn't even flinch. Orbital tracking systems, from NASA's Deep Space Network to independent observatories in Japan, France, and Australia, confirmed that Atlas maintained its pre-impact vector with near-perfect fidelity. There was no acceleration, no deceleration, no drift. Its calculated path through the ecliptic corridor remained entirely intact. This means one of two things. Either the flare's mass and energy were dramatically less than previously measured, which contradicts solar observatory data, or Atlas has a way of absorbing and redistributing energy without letting it affect momentum. The second possibility is deeply unsettling. Orbital compensation is a feature found only in engineered systems. Satellites, probes, spacecraft, anything that can course correct or dampen external forces. Natural objects do not compensate, they react. So either Atlas is extraordinarily dense and symmetrical, resisting all external push, or it possesses a structure that allows it to neutralize impact force. Both options suggest control, not chaos, design, not drift. And if this object is managing its motion through interstellar space, then someone, or something, once made sure it could. Since its first observation, one of Atlas's strangest features has been its heartbeat, a light cycle that repeats every 16 hours and 16 minutes. The consistency of this cycle has fascinated astronomers and engineers alike. It pulses like a beacon, not random, not fluctuating, a clean wave pattern visible across multiple instruments. When the solar flare struck, many expected this cycle to deform. A sudden injection of energy, even a minor one, should have altered rotation, reflectivity, or surface temperature. Such shifts normally show up as slight irregularities in timing or intensity. But Atlas's pulse remained unchanged. The 16-hour interval stayed locked, like it was being regulated by something internal. There was no drift, no delay, no increase in amplitude. Even the flare's impact, which lit up the surface briefly, didn't disrupt the underlying signal. This reveals something vital. If the heartbeat is caused by rotation, then that rotation is astoundingly stable, resistant to external torque or heating. If the cycle is instead related to reflectivity patterns or internal processes, then those processes are shielded or inertially insulated. Whatever the mechanism, it appears decoupled from the surface. This kind of cycle regulation is virtually unknown in the natural world, especially in objects with no atmosphere, no magnetic field, and no observable mass ejection. It's the kind of consistency you find in engineered systems, lighthouses, transmitters, beacons. The implications are profound. Either this is a natural resonance of a structure we don't yet understand, or it's a signal, regular, patterned, and precise, built to endure disruptions from the outside. Even a solar flare couldn't mute it, which means we're not watching random noise, we're listening to something persistent,